Kia ora Year 12 and 13. This is a factorial proof question for Elsie, and it's got two different ways of doing it. One of the ways you can do this is with a kind of direct proof method, and the other is using induction. It's quite a hard problem to see what to do to start with if you haven't got your eye in for factorial problems. So we look at the left-hand side first. We've got 1 times 1 factorial, plus 2 times 2 factorial, plus 3 times 3 factorial, and so on. And we have to show that that equals this very simple expression on the right. So what is stopping this being easier is that I can't simplify 1 times 1 factorial or 2 times 2 factorial. If instead, though, I had 2 times 1 factorial and 3 times 2 factorial, then that would simplify to 2 factorial. This one would simplify to 3 factorial, and so on. So the direct way to get here with this one is to force those simplifications into the left-hand side. It's a bit like when we do completing the square. We're going to add something in, and then we're going to take something out. So we'll start by rewriting the left-hand side, or just a wee bit of it. And we'll say that instead of having 1 here, we could write 1 as 2, but then we have to take away the extra 1 that we've put in. Instead of writing 2 here, we could write 3, but we've added in 1, so we'll have 3 take away 1. Instead of writing 3 here, we could put in 4, take away 1. So let's do that. So it looks worse to start with. So we're going to have 2 take away 1 times 1 factorial plus 3 take away 1 times 2 factorial plus 4 take away 1 times 3 factorial, and then the last term will be plus n plus 1 take away 1 times n factorial. Now we're going to expand some of that out. So we're going to have 2 times 1 factorial plus 3 times 2 factorial, and so on, 4 times 3 factorial, plus n plus 1 times n factorial. So what have I got dealt with there? Well, I've done this bit, this bit, this bit, and this bit. And now we've got all of these terms to take away when we do the rest of the expansion. Right, so we're going to have take away 1 factorial, take away 2 factorial, take away 3 factorial, take away n factorial. Okay. Cleaning up the first bit here, so this line here gives me 2 factorial plus 3 factorial plus 4 factorial plus dot 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 n plus 1 factorial minus 1 factorial plus 2 factorial plus 3 factorial plus all the way up to n factorial. So now you can see that we're just about there because a whole lot of things are going to simplify away. So I'm going to write that out so that you can see what's going on. I've got 2 factorial plus 3 factorial plus 4 factorial up to, and then I've got plus n factorial plus n plus 1 factorial minus 1 factorial minus 2 factorial minus 3 factorial minus 4 factorial all the way up to minus n factorial. So what does that leave me with? Well, here 2 factorial minus 2 factorial goes 3 factorial minus 3 factorial, and so on. We get left with this, which is really good because it's what we're wanting. So that's n plus 1 factorial. And then if you're looking down here, all of these have gone except for this one here. So we've got n plus 1 factorial, take away 1 factorial, and 1 factorial is just 1. So that's the direct proof way. Done in 4 minutes. Now I'm going to show you how to do it using induction, right? So let's go back to the start and see where we're trying to go again. So I think induction is probably more likely to work. It's, I think, a little bit more work. But the method of induction goes like this. First we're going to have a proposition, right? And we're going to say that the proposition for case n is this, that 1 times 1 factorial, so it's the thing we want to prove, right? What we're going to do is to assume, step 1 is to assume that this is true for some n, and n is an integer. Then the tricky bit is to show that if p of n is true, that this implies that p of n plus 1 is true. In other words, we're going to start with what we're assuming is true, and we're going to do something to it and show that we end up with the proposition for case n plus 1. Okay, and when we do induction, that's often called the inductive step. That's a bit where you've really got to use your brain. And then we're going to go back and say, well, let's look at whether it's true for a really simple case. So we're going to show that p of n is true for n is equal to 1. Therefore, it must be true for n equals 2. Okay, so we've already started by writing out what p of n is, right? So that's my starting point. It's always good to write out p of n plus 1 because that shows us where we're trying to go. So p of n plus 1 is this, 1 times 1 factorial. But this time we're going all the way up to this case, and here we're going to have n plus 1 factorial minus 1, so n plus 2 factorial minus 1. So we assume that p of n is true. So let's write out what that means again. So this is my starting point, this equation here. So let's think about what we have to do to get from here to get to this left-hand side. Well, we have to add in one more term. And if we're adding it in on one side, we must add it in on the other side. That's just year 9 algebra. So we can say that 1 times 1 factorial plus 2 times 2 factorial, and so on, plus this extra bit is equal to n plus 1 factorial minus 1 plus the extra bit, right? So we're just adding that term onto both sides. And now what we need to do is manipulate the right-hand side, so manipulate this bit to show that we're going to end up with this. And it's pretty simple. If we reorder, we can get this, n plus 1 factorial plus n plus 1 times n plus 1 factorial, take away 1. Right, so that's that bit, then that term, and then that one. We can take out a common factor here of n plus 1 factorial. So we've got one lot of them here, and we've got n plus 1 lots of them here, take away 1. So that gives me n plus 2 times n plus 1 factorial minus 1, which is n plus 2 factorial minus 1 as required. So what have I just done? Well, I've shown, so we have shown that if p of n is true, then p of n plus 1 is also true. Now let's go back and look at n equals 1. What's the case here? So the left-hand side of Pn is just 1 times 1 factorial, which is 1. The right-hand side of Pn is 1 plus 1 added together, factorial, take away 1, which is 2 factorial. 2 factorial is 2. So we've shown that the left-hand side and the right-hand side are equal. which means that the proposition is true for n equals 1, which means it must be true. So we've shown that P of n is true for all n, which are integers. Okay, that's just shorthand meaning for all, and that just means integers. So there we go. So that's doing it using induction. I think if you're comfortable with induction, it's definitely an easier way to do this problem, but it is a bit more work. I really like the direct proof method. So let me know if you've got any questions on that, or if you come across any other similar proof questions that you'd like me to go over.